Hello everyone, welcome back. Hopefully everyone's sufficiently caffeinated after yet another tea break. First up, I'd like to thank our bronze sponsor, Corelight. So Corelight transforms network and cloud activity into evidence so that data-first defenders can stay ahead of the ever-changing attacks. As delivered by their open NDR platform, Corelight's comprehensive correlated evidence gives you unparalleled visibility into your network. And with that, I'll hand over to Shelly Raban for Who Watches the Watchmen.
Hi, everyone. Thanks for being here. I'm really excited to talk here for the first time. What if I told you that the very tools we rely on to secure our cloud environments expose us to new risks? Today, we'll explore how attackers can abuse policy as code engines and IAC tools and what you can do about it. Hi, I'm Shelly. I'm a senior cloud security researcher at Tenable. I have 7 years of experience in cybersecurity. I've conducted threat hunting, malware analysis, detection engineering, and more. And some fun facts about me: I love cuddling with my cute cats and cooking vegan food. I've been vegan for the past 8 years and still standing. We'll start with an introduction to the IAC world, then dive into my research process and malicious techniques. We'll then look at my analysis of thousands of Terraform modules, and wrap up with some conclusions. Infrastructure as code, or IAC, is the de facto method for provisioning and managing infrastructure at scale. But policy as code is a less familiar concept. Policy as code is the use of code to define rules and conditions. You need some kind of programming language to write the policies, and a policy engine to run them. One common use case for policy as code is for governing IAC. Usually, you host your IAC in some kind of version control system, such as GitHub. Then, when you update your code, it undergoes a series of tests. Among them, your security and compliance policies run by your policy engine. Finally, if all the tests pass, your code deploys resources in the cloud. This made me think, if an attacker gains access to the supply chain of your policies, what can they do with it to compromise your cloud environment? OPA is the go-to open source policy engine. It is general purpose. You can give it any kind of JSON input and get back a policy decision. It is commonly used for authorization in cloud-native applications and admission control in Kubernetes, like we just saw in Shai's talk. And when you use OPA, for example, your application can query it to check whether a user is allowed to perform a certain operation or whether inbound traffic is allowed via a certain port. And OPA does the policy evaluation and returns a policy decision, which your application is then responsible for enforcing. When you use OPA, you write your policies using Rego, a high-level declarative language. And we will soon see you can use it to do some pretty bad things. We've all heard of Terraform, so just to be on the same page. Terraform is the most common IAC tool. It used to be open source, and now it is source available. Terraform is cloud agnostic, so you can use it with any cloud or SaaS provider that exposes API. And in Terraform, you write your configurations in Hashicorp Configuration Language, or HCL, also a high-level declarative language. Terraform has two main components: modules and providers. You can think of Terraform modules like Python modules. They encapsulate sets of configurations into reusable units, and they can be shared. And these are written in HCL code. Providers are compiled binaries that are responsible for interacting with the remote cloud or SaaS APIs. And the core Terraform workflow consists of three main stages: init, plan, and apply. Init is where you fetch your dependencies locally, including all the required modules and providers. Plan is where you create a diff between the state in your code and the current state in the cloud. And apply is where changes are taking place. And remember these 3 stages, as we will soon see why they are important. Let's dive right into the malicious techniques, starting with OPA. Let's say you have an OPA server, and it's configured to fetch policies from an S3 bucket, and a web application that uses OPA for authorization. In our attack scenario, the attacker gains access through a compromised IAM user, and the only required access here is write access to the bucket holding the policies. The attacker uploads a malicious policy to the bucket, and the OPA server fetches the updated policies. The next time the web application triggers a request to OPA, policy evaluation takes place, and that's where bad things happen, because this time the malicious Rego file runs as well, and it may, for example, exfiltrate cloud credentials to an attacker-controlled server. When I started researching OPA, I ran into these built-in functions. They handle basic tasks like manipulating strings and numbers, as well as more advanced tasks like signing requests to AWS. And I found these interesting for my research. So how many are there? Well, sorry, quite a lot. So I looked up some previous research, and I found it very surprising that there is a serious lack of awareness around this topic. I could only find a single blog post talking about the malicious use of Rego. And in his blog post, Liam Galvin talked about 2 specific risky built-in functions, the OPA runtime function and the HTTP send function. You can use the OPA runtime function to fetch environment variables, and these may include cloud credentials, and the HTTP send function to send an HTTP request. So he described how you can leak these environment variables or the whole Terraform code that's passed as an input to OPA. OPA has the capabilities feature, which allows you to restrict the use of certain built-in functions and fail policies that use them. But it's important to note that in the default configuration, all functions are allowed. But the HTTP send function and the OPA runtime function got some bad attention. And if an organization has some kind of security awareness around OPA, I believe these are the 2 functions it would block. So this sparked my curiosity. If an organization prevents the use of the OPA runtime function, can I find another way to extract cloud credentials? Then I thought, OPA commonly runs on an EC2 machine, which may have a role attached to it. So maybe I can use Rego to contact the IMDS and fetch the credentials of the cloud role, and finally leak them out to my external server. So I wrote the Rego code to do that. And basically, I took the batch version from the AWS documentation and translated it to Rego. And I used the HTTP send function for this. As you can imagine, you shouldn't allow policies to access other internal servers, especially if you use policies from third parties. So I ran this Rego code, and success! I was able to leak credentials from the IMDS to my external servers using OPA. Let's see a demo. So our OPA server is configured to fetch policies from an S3 bucket. And the attacker is listening on HTTP. The attacker writes the Rego code to contact the metadata service, fetch the creds, and leak them out of the environment. And finally, he uploads this malicious policy to the bucket holding the policies. The next time the web application triggers a request to OPA, policy evaluation takes place, and this malicious policy runs as well. And it leaks credentials to this external server controlled by the attacker. Thank you. So Then I thought, what if an organization prevents the use of the HTTP send function? Can I find another way to leak data outside of the environment? The net category caught my eye. Sounds like networking. So I looked into the documentation again and looked through all the built-in functions. And one specific function caught my attention: the net lookup IP address function. It receives a domain name to resolve and returns an IP address. So I thought, what if I look up a domain under the attacker's control and monitor the DNS requests? So again, I wrote the Rego code to do that. And this time, I concatenated an access key that was hard-coded in the input Terraform configuration as a subdomain of my malicious domain. I passed this domain string to the net lookup IP address function, and finally ran this Rego code. And success! I was able to leak data outside of OPA using DNS tunneling. And I did so with using a function that's not likely restricted by many OPA deployments today. So this was a very exciting moment. So up until this point, we've talked about techniques in OPA, which is a policy engine. Now let's talk about Terraform, which is an IAC tool. I wanted to see whether similar techniques apply to Terraform, since it also uses a high-level declarative language, HCL. Terraform has data sources, which allow you to fetch external data to be used throughout your configuration. And one cool thing I realized is that data sources run at plan time. Recall the 3 stages we talked about earlier: init, plan, and apply. You may think that the plan stage is read-only, but actually, code gets executed during this stage. And it was mentioned briefly by Rami before. That was a really interesting discussion. And actually, there was a cool blog post about it. But I wanted to add that you don't have to write a custom provider to do that. We talked about the difference between modules and providers. So providers are compiled binaries written in Go. And you can use HCL modules, and this really lowers the bar for attackers, because you can actually use existing providers' data sources instead of writing your own. So for example, you could use the HTTP data source to, for example, leak sensitive HCL parameters from your configuration to your evil domain. For example, you could also use the external data source that runs custom code on the machine running Terraform. So Hashicorp states that this external data source is only an escape hatch, and you shouldn't really be using it for legit use cases, only for very specific ones. So for example, you could use this for your evil script to exfiltrate the env command results to an external server. Terraform also has provisioners, which allow you to run code on the machine running Terraform or the newly created infrastructure. And again, Hashicorp states in their documentation that provisioners should only be used as a last resort. For example, you could use the local exec provisioner to run code on the machine running Terraform. You could, for example, fetch an external payload, grant it execution privileges, and finally execute it. Or you could use the remote exec provisioner to run code on the newly provisioned infrastructure. For example, you could run a coin miner on the newly created EC2 machine you just created. Then I thought, why not try my DNS tunneling in Terraform as well? I found this DNS data source, and it allows you to look up a host and also returns an IP address. So I concatenated a secret string from my configuration as a subdomain of my malicious domain. I monitored the DNS requests and ran this Terraform code. And success! I was able again to leak data using DNS tunneling, this time in Terraform. What about extracting credentials from the IMDS? I wrote the HCL code to do that with the HTTP data source. But this time, I got an error, because the HTTP data source does not allow the put method. It only allows get, head, and post. So this is yet another reason to use IMDS, which requires the use of the put method. So now we know various ways attackers can abuse Terraform. Let's focus on the main entry point, third-party code. I wanted to see whether attackers had already published such third-party code to the public Terraform registry. So I defined the different risks we've just talked about using Python and scanned all the modules in the registry against them. I calculated the percentage of modules that each block type appears in, and this is what I found. The DNS data source and the external data source are the least prevalent. They rarely appear in Terraform configurations. So if you bump into one of these in your organization, it's an artifact worth looking into. And to avoid causing alert fatigue, I suggest you start by detecting these anomalous blocks first. We now detect these in Tenable Cloud Security. One specifically interesting module got detected during my analysis. It had a weird-looking domain and a sensitive HCL parameter inside the request. And I found out this was another researcher's POC, demonstrating how you can leak data outside of Terraform. And look, it seems completely legit in the public Terraform registry. It was even assigned the AWS logo only because it uses the AWS provider. And it has almost 3,000 downloads, which is a fair amount of downloads for a POC. So I wonder whether these are all scanners or researchers like me, or actual victims that fell into this trap. Now, let's see what some common IAC scanners have to say about our malicious HCL configurations. You might be surprised, but the most common scanners almost always fail to detect the risks we've just talked about. I used Chekhov, Trivi, and Kix in my analysis, and the results were disappointing. The industry is behind. One vendor suggests here that instead of leaking secrets over HTTP, you should leak them over HTTPS, which is a very dangerous recommendation. And I won't mention the vendor's name, but this is pretty crazy. And it's crazy how unexplored this area is, that even security vendors who scan IAC get it wrong. Another vendor suggests that you remove this potential exfiltration HTTP request, while actually highlighting an SSM parameter block, which has nothing to do with HTTP. I really wish security vendors would step up their IAC security game. Before moving on to the mitigations, I wanted to quickly talk about a vulnerability I found during my research that didn't make it into this presentation. I played with the different inputs that OPA gets, and I found I can pass a UNC path instead of a Rego file. And when OPA runs on Windows, if you pass a remote share controlled by an attacker, you authenticate to that remote share over SMB. And that's where your NTLM creds of the logged-in user are passed to the target server. And the attacker can catch these and use them to relay the authentication or crack the password. I won't dive too much into the details. You can read all about it in the upcoming blog post, but I did want to give a huge shout out to Styra, the maintainers of OPA, that were super cooperative in working on this, and within a few weeks of my initial report, they published the fix, and it is now available in the new release of OPA. Thank you. Let's talk about some mitigations. Only use Rego policies and Terraform providers and modules from trusted sources. Also, verify their integrity. Both OPA and Terraform have built-in features to do that. Set up granular RBAC with least privilege, both at the application level and in the cloud roles and machines. Also, set up logging to analyze and monitor the activity. limit the capabilities and network access of these applications and machines, as the default configuration is often insecure. And if you remember just one thing, remember this. Scan before you plan. The plan phase is not read-only. Place your scanner before this phase to identify security risks before execution. And let's talk about some key takeaways I had from my research. Look beyond IAC misconfigurations. Check for code execution and network activity done by non-resource blocks, especially if you use third-party code. I recommend you explore less researched areas, like OPA, for new attack vectors and vulnerabilities. And finally, research open source tools, as many IAC and PAC tools are written in Go and are easily readable. And they also have active communities and a responsive security team. Thank you so much for listening. I'll be glad to take any questions, and also feel free to reach out to me on Twitter.
Right. So we have had a question or two on Slack. So to start with, for the Terraform-based exploitation vectors you've been talking about here, is this something you can do to harden the Terraform plan stage when you're executing it? Can you do that read-only, or does that break it? Is that a viable mitigation there?
Okay, good question. So the question is around like the hardening the Terraform plan phase to not allow the risks we talked about. Yeah, you definitely can grant Terraform read-only role. Of course, if you use it for other things, you should make sure you don't break anything, but you can separate the role of the plan phase from the apply phase. Yeah.
Makes sense. We've got another one here. Have you talked to Hashicorp at all about doing a static analysis of the Terraform registry as a whole? Is that something that's been on your radar?
So I haven't talked to Hashicorp about it. Actually, I just used the public API and did my analysis locally. Yeah.
Okay. And with that, let's take a look around the room. Have we got any questions from the audience? Oh, yeah. Right at the back. Yeah, we've got a microphone coming over.
Thank you for the talk. It was very nice.
Thank you.
Have you thought about using, for example, mutation hooks on OPA? Well, Gatekeeper, basically. So it allows you to modify the JSON that enters, and you can generate JSON, basically. So that might be something also to explore in Kubernetes a little bit. I was thinking about when you mentioned all of this.
Sounds very cool. I haven't played with that, actually, but really good idea.
We've got time.
Got one more.
Oh, fantastic. There we go.
Hello, this was great, right up my alley. Does OPA have a similar registry as Hashicorp by any chance, or is there a common shared source of rules? Did you consider like pollution vulnerabilities or watering holes in OPA? Because I know you covered that for Terraform more.
Interesting. So I haven't bumped into such registry. There are like active communities and a lot of integrations going on with OPA. So for example, Gatekeeper is very big, and I believe they have a repo of policies, but I'm not aware of something more structured than that. Yeah. But that's a very cool idea for further research, for sure.
Okay. In that case, I think we'll wrap it up there. Thank you very much again, Shelly.
Thank you so much.